Right. Now that we have got a basic understanding of what happens in an electrochemical reaction, we've got a basic understanding of what is known as the standard hydrogen electrode potential. We can now move on into our Pobe diagrams. Okay. So, um, what are our Pobe diagrams? Okay. Um, Before we see the Pobe diagrams, it is important to note that thermodynamic data can be shown more conveniently using what are called predominance diagrams. What are predominance diagrams? These are diagrams that only show specific dominant species, species that have got the highest activity in certain conditions, and then these are the ones that are displayed in the predominance regions in terms of appropriate variables. So in terms of your appropriate variables, in our case we are talking of the potential, in your case we are talking of the electrochemical potential and the pH. Okay, those are our variables. So you typically use these to construct these predominance diagrams using this threshold of predominance. Okay, so it is important to note that these are more of predominance diagrams. Okay, and they are simply showing the dominant species. It does not mean that there are no other species that are available, or it does not mean that there are definitely no other species that can occur together with the dominant species in that region. It simply shows the predominant species for a certain now this is a relative depiction of what is known as your Pobe diagram or EHPH diagram. So here you've got your potential, and here you've got your pH. Okay, so what it is simply showing here, there is your acid in terms of pH, and then there is your base here. Okay, in terms of your metal, you can here metal in this region. You've got your metals with the lowest state. As you go up here, the oxidation state of your metals actually increases. Okay, then you've got some other soluble species, etc., shown in these different regions. So we'll try to explain what this diagram is basically trying to tell us. So Pobe diagrams show thermodynamic stability of species in aqueous solutions. Okay, so they are very pivotal in designing parameters for metal extraction, especially in your hydrometallurgy. Okay, um, the system can actually, in a diagram, can contain several species, actually, your dissolved ions, your oxides, such as in your hydroxides, etc. Okay. Now, what are the uses what are the uses what are the uses of your Pobe diagrams in hydrometallurgy? So the first use is to specify conditions except for your leaching, that's selective dissolution or selective leaching, and also you also need to specify some conditions for precipitation of your metals. Could be usually in the form of hydroxides. Okay. Then also important in corrosion engineering, they used to analyze the dissolution and passivation behavior of different metals in aqueous environment. Also tell us the regions where a metal is unstable and it is also bound to corrode. Okay. So they generally also show stability areas of species in redox potential and pH environments. Okay, so you need to know if you're working in an environment that is pH high or low, high potential or low. You need to know which species are actually stable in that. So basically, this is the starting point of your Pobe diagram. We are not looking at the basic regions of your Pobe diagrams. Okay, so as we say here, we've got your potential, and here we've got your pH. Okay. So we can say, of course, the pH 7 is considered to be the neutral pH. So we can say here we've got your acidic pH above 7. You can actually call it the alkaline conditions. Okay. Then now this is your potential at potential 0. Okay. Below potential 0, we can say that these are reducing conditions, and above potential 0, we can say that these are oxidizing conditions. Okay. So we can actually depict our Popper diagram. We can separate it into 4 even more, and we can say that this is below 7, below 7, below 0, reducing acidity. Okay, above 0 but below 7 is now in oxidizing but still acidic. Okay, above 7, below 0 is alkaline but in reducing condition. And above 7 and also above 0, you can also now, these are oxidizing alkaline conditions. Okay. So generally, your Popper diagrams, they consist mainly of 3 lines. Okay. So you've got your horizontal, vertical, and diagonal lines. So your horizontal lines, okay, your horizontal lines. Okay, so your horizontal lines represent represent reactions that are involved with electrons but are independent of EH. So this is an example of your an example of your an example of your horizontal line. So we are saying it is independent of pH. Why? As you increase your pH, nothing happens to the value. It remains consistent. Whether at pH 1 or at pH 14, it is independent of pH. Okay. So these are reactions that are mainly involved with the electrons. How about your vertical lines? This is an example of a vertical line here. Okay, this is your potential here. So these lines represent reactions that are involved with your protons or your hydroxide, but are independent of potential. In other words, here, if potential is not involved, electrons do not participate. There's only either protons or hydroxide ions that are participating. So they are independent of your potential. So you can see here this vertical line here. As you increase, if you increase your potential, maybe from 0 here, there's 0, from minus 0, whatever, into positive, it remains constant pH. There's always a constant pH. Nothing happens to your pH as you increase your potential. So it means that they are only involved with your proton exchange or hydroxide ions, and there is no electrons that participate in these reactions. This is independent of EH. However, you can also have some diagonal lines, whatever, that are slanted anyway. These reactions are involved now with both your electrons and both your protons or your hydroxide. Why? Because there is change. If you increase something, if you decrease your potential, maybe you also decrease your pH. There is a correlation between the two. So it means that both electrons and protons are involved. Okay. So this is an example of your Popper diagram for ion water system. Okay. This is an example of your ion water system. So we can show that in this region here, the Fe3 plus ions are actually more stable. Okay. And if you remember well, we said oxidation state increases as the potential goes. So here Fe3 plus, we assume that this is the highest oxidation state for ion in these conditions. Okay. Then this is your Fe region stability for Fe2 plus. Okay. So as you go down, the oxidation state also reduces. And then lastly, this is your Fe0. Okay. It's the regions of stability for your Fe0 here. Okay. So Fe0, Fe0, Fe2, and Fe3 plus. We are increasing the oxidation state of our species. Okay. Then here, this is the region of stability of our hydroxide or of our oxide, sorry, our solid, which is your maybe your precipitate. Okay, these are the regions of your stability of your oxides. Okay, so this is the Pobe diagram. So it's simply telling us that in this region here, for example, this region, the predominant species is actually your Fe3 plus. Okay, it does not mean that Fe2 plus is not there, but it simply means that the predominant species in this case is your Fe3 plus. The same again here, this is your Fe0. It does not mean that you don't have any Fe2 plus or Fe3 plus. It simply means that the predominant species in these conditions will be your Fe0. The same again for the other conditions. So you can see here, we can actually divide this Pobe diagram into three regions. So this is your A, your B, and your C. So your A is actually called the acid lake, and then your B is called the basic lake, okay? And then your C is actually called the complexing lake, okay? This is simply based on the position in the Pobe diagram, okay? Then we also have got these lines that you can see, the blue lines that you can see, the blue dotted lines that you can see depicted as 1 and 2. These are blue lines. What are these blue lines? These are blue lines that show a region of stability of water. So between these two lines, this is the region where your water is very stable. Okay. So what are the equations of this line? For example, line number 1, this is the equation of this line. So if you are saying this depicts the region of water stability, it means that below this region, water is formed. Okay, below this region, water is very stable. And above this line here, it means that there is now evolution of HO2 gas, because this reaction goes to the sort of to the left. Okay, and then if we go down again, um, this region below this up shows again water stability, and below this region, this a region which shows possibility of your hydrogen gas evolution. Okay, so these lines here in between them, they show water stability region, and this is the region where we want to do most of our leaching, most of our recovery, because remember, hydrometallurgy is supposed to be done in aqueous state. Okay, all right. Okay, so this is what I've explained in the previous slide.